Okay, now let's see how we get a bid price from this linear program. In linear program, there's something called the shadow price. It's also called the dual variable and some other things, but we're going to just use that term, the shadow price. And we're going to take the shadow price on this constraint, on the capacity constraint. A lot of times that's called lambda. That looks like an upside down Y. A lot of times that's called lambda. So we're going to take the shadow price on this capacity constraint, and that is going to become our bid price. So let's see what that means. Let's see if I can write down here. So there's something called the shadow price, and that is going to be our bid price. Now the shadow price, the definition of the shadow price is if you have any linear program and you have a constraint, if you were to change the value of the constraint by 1 unit, the resulting change in the objective function, the value of the objective function, would be the shadow price. So for example, a lot of times this is explained with a simple lemonade business. So there are lemons, and from those lemons and some water, you produce lemonade. Well, in order to maximize revenue, the lemonade stand determines the price and how much lemons or lemonade they're going to make given some number of lemons. So there's some constraint on the amount of lemonade they can make given the number of lemons that they have. So that would be, in our case, this constraint here. Well, if the company wanted to increase revenue by purchasing new lemons or more lemons, they would want to analyze whether that made sense in terms of the return. So if they could buy an additional lemon for, 50 cents and make $1 extra in their revenue, then that would be a good business decision. If a 50-cent increase in their cost of lemons only resulted in a 40-cent increase in their revenue, then that would not be a good business decision. So that change in revenue resulting from the additional lemons is the shadow price. And normally businesses use this to analyze whether they should make changes in their constraints relative to their objective function. So that's how it would work in a lemonade stand. It's not much different in an airline's network. Our constraint is seats. So let's say we had our capacity for some leg was 100 seats, and we produced a certain amount of revenue from that seat. So for a particular leg, there's many other legs in the network, but from a particular leg there's 100 seats. If we change this, if we said there's only 99 seats, or conversely if we added a seat and said there's 101 seats, but let's take this, so we decrease the capacity by 1 seat, there would be some change in the value of the objective function. And that change is the bid price or the shadow price that comes from this constraint. From that bid price, we get a value of that incremental seat. So now I know how much the 100th seat is worth to the airline. So using that, I can set a hurdle rate for the fare that I'm willing to accept for that seat. So if the bid price is $150 and a customer comes along and is willing to pay more than $150, then we would accept that customer. If the customer is willing to pay less than $150, we would turn that customer away because the bid price tells us that the seat is worth $150. In other words, our demand forecast has valued that seat at $150. So now we have a hurdle rate that we can use to make a decision. So that becomes our decision variable. So let's take a look back at our sample network and see if this makes sense. So let's look at this leg here. This old bid price is no longer relevant, so I crossed it out. Let's say we have these fares, and the itinerary in this case is just one leg, so to make it simple. And at this point, we have 99 seats left to sell, remaining capacity of 99 seats. And let's say at this point, we know that we can sell the 99th seat for $325 to this customer. So we have a forecast, and we're convinced that there's a customer willing to pay $325 for this 99th seat. If we then take that seat away and only have 98 seats, that 99th seat, that opportunity cost of selling or not having that seat to sell was $325. So if we were to go from 99 to 98 by selling a seat, so we're changing our remaining capacity by selling seats, as we reduce our remaining capacity by 1, we know that seat is worth $325. So we would only be willing to sell that seat if a customer is willing to pay more than $325. If they were willing to pay, or if they were only willing to pay less than $325, then we would reject that request and save that seat for a higher paying customer because we know that customer is out there. So now you can see the result is that the bid price in this case is actually $325. And if we were, running our linear program, and it is deterministic, so we're saying we know with certainty that a customer is out there willing to pay $325. Our bid price, our shadow price on this capacity constraint would be $325, and that becomes our hurdle rate or our bid price for that leg. Now notice one other thing while we're here. When I formulated the linear program, I had a capacity constraint, and I said there were, let's assume there's 100 seats of physical capacity on the aircraft. That would be the case only when no seats have been sold yet on that aircraft. As we sell seats, we need to come up with new bid prices for the actual remaining capacity. So throughout the selling period, the remaining capacity changes. So let's go back to that. So don't take, where is it? So don't take this to mean that this is the physical capacity and we're always calculating a bid price off of the physical capacity. Each time we run this model, this constraint will actually change for each leg J, because as we're selling seats, the remaining capacity changes. So now just to complete from our example of there, so we would have a bid price for leg J in the way we looked at the example above of, I think it was $325, right? And then we would have J through, or I don't know, 1 through N or something, a vector of bid prices that we would then upload to the reservation system. And as requests come in, the fares would be compared to the bid price, and the decision to accept or reject that fare would be made in real time. Now, you might be familiar with reservation systems and know there's actually allocations or the number of seats the airline is willing to sell at a certain fare on a flight is in the reservation system, even though it's a bid price system. So what happens is, and maybe we'll do this at in a later video, there's a way to convert this bid price into the number of seats we are willing to sell. So perhaps the bid price is $325 for the 99th seat. It's also the bid price for the 98th, 97th, 96th, and so forth. Then we would be able to say that the bid price or the number of seats we're willing to sell at $325 is 3 or 4 seats. And that's why in the reservation systems you do see a discrete number. You don't see the bid price, but actually those calculations are happening in near real time, so that the number of seats the airline is willing to sell is updated based on updates from the revenue management system or updates from sales that are occurring throughout the network. So before we leave, let me just point out a couple of things on the usefulness of this type of model. So let's start with the fact that this is deterministic. So we said, no, this is a simple linear program. It's deterministic. So we are assuming that we know with certainty how many customers would be willing to pay a certain fare for each itinerary. Well, in reality, if you know exactly what your demand is, your problem, your business problem becomes pretty easy. Well, that's really not the case, is that we can't forecast the future with certainty. So that becomes an assumption that a lot of RM scientists have a problem with, because it really is not, we call these models, right? We're trying to model the real world. Well, if you're assuming something that is that far from reality, then that doesn't seem like an accurate model of the actual behavior that's happening out in the real world while customers are purchasing airline tickets. On the other hand, what's really important is the accuracy of the bid price, right? So even if you have a problem with the assumptions, if you're getting a good answer, then the other view is, well, airline managers are not RM scientists. All they care about is maximizing revenue. So if they can get a good bid price from a simple linear program, then that might work for them. The experience I've seen in the airline industry is I have seen this model used. Primarily, I've seen it used to come up with bid prices which are also displacement costs that are used in virtual nesting systems to adjust the fare levels for the displacement that's occurring on other legs in the network. I'm not going to go into that. There's a video on virtual nesting, but this is not a bad way at all of coming up with displacement costs for virtual nesting or other heuristic bid price methods. The other thing I'll point out here, and it's not unique to this model, but this is somewhat static. So we are going to get accurate bid prices and accurate objective function value at the time we are solving this model. But the airline, the real environment for an airline is changing constantly. So by the time we finish running this model, the remaining capacity has already changed because people are constantly buying seats. Also, the forecast of demand is changing because as airlines get more information, the remaining demand changes quite rapidly. So we need a mechanism. So if we were to just load this into the reservation system and say our bid price is $325 and left that bid price there for a couple of days, it becomes stale very quickly. It's only accurate at the time it's calculated. So you need to consider, one, how often you can run this model, or two, how you're going to adjust that bid price for changes in the remaining capacity between optimization runs. And there's something called the gradient, which we'll perhaps get into in a later video, that we can use as an approximation for the changes of bid prices as the capacity constraint changes in between optimizations. I hope that made sense. I'm not sure it did, but the point is, when you run a model like this, you get an accurate answer, but the answer is only accurate for a very short time. So you need to consider how you're going to update the bid prices in between optimizations. One of the real advantages of EMSR or even heuristic bid price is you can run them very, very often. You could run it every time you sell a seat. These network models take time to run, and that's not practical. Okay, so I think that's it for now. Next, we're going to get into a more sophisticated model. We're going to look at changing this constraint from a deterministic demand constraint to a stochastic demand constraint. So in other words, we're going to put some nonlinearity into this demand forecast. It's going to be a probabilistic function instead of a static forecast. And then this objective, or the whole linear program, becomes a nonlinear program, and we have to use calculus and probability functions and all sorts of fun things to get the model correct and come up with a solution. So the next model we'll look at is nonlinear program. Hope to see you there.